C. So the title of part 5, you want to check? It's called Ordinary Stoichiometric Calculations. Okay, so there's this other sort of calculation you do, what I call on the front end of an ordinary stoichiometric calculation. Basically, it's called limited supply stoichiometry. You'll see what I mean. You need to identify what's which reactant you're going to run out of first, which reactant is present in limited supply. So I was thinking how to describe this semester, and I came up with this. So like if we have a reactant A and a reactant B, okay, it goes to form something. We'll just call it C. So one of these two, A or B, is usually in limited supply. Okay, that means you're going to run out of it first. Okay, the other thing, or if there was another reactant D, E, okay, everything else is present in excess. Okay, and so that's it. So we have the limited supply reactant and the excess supply reactant. Now if you had 3, like I said, 2 would be excess and 1 would be limited supply. If you're like me, I was at my office, I'm like, well, there is one scenario in which, and they call it, and we do this in titrations, that basically you had just the right amount of everything. Nothing left over, okay? That's definitely a possibility. Okay, but usually one's in excess, you know, like your HCl and your sodium bicarbonate was in excess, and one's limited supply. So what we're going to see is that all the limited supply stoichiometric calculation is to identify which one is in limited supply. That's it. That's all I need to talk about right now. Identify which one. Now, if you're like me, once you get to see what these problems are, you're like, well, I got a 50-50 chance of saying either A or B. So on your unit exam for this material, you will have a problem where you have to say which one is in limited supply. And you have to justify your answer. Just guessing does not do it. There's different ways to identify the limited supply reactant, and I'll show you some of my favorites. So not necessarily chemicals, but if we start with making a ham sandwich, kind of a simple ham sandwich, and you might recognize the 2, 1, and 1. Those are like stoichiometric coefficients. So we could have this scenario where, and I'm going to call this the have amounts. Okay, specifically, we have 20 slices of bread, and we have 7 slices of ham. And, you know, right off the bat, one of the questions is how many sandwiches can we make? Well, you might start to kind of do some ciphering. Looks like I could make, 10 sandwiches out of that. Or I could make 3.5 sandwiches, 7 sandwiches out of that. Do you see where I'm kind of going with this? Seems like you can only make 7 sandwiches. Does that seem right? Just eyeballing it. So in this scenario, actually, ham is limited. And you're right. And there's certain questions that can kind of come from that. So which reactant is in limited supply? Ham is limited. Bread is excess. Let's see, how many sandwiches can you make? 7. How many slices of bread will you use? Well, it looks like 14. Do you buy that? Me too. So we'll use 14. Okay, so how many will we have left over? Well, let's see, 20 minus 14 is equal to 6. So that's kind of a bird's eye view of kind of what we're going to do with chemicals coming up. So these slides kind of talk you through it. Now, what I like to do is come up with a need ratio and a have ratio, just to identify ham. So with ham's the limited supply reactant. That's what I'm going to kind of show you here. So the have and have-nots, okay? My have ratio, my need ratio actually comes from what's going to be the stoichiometric coefficients. Okay, the ratio of what you have to have. We have to have 2 slices of bread for every 1 slice of ham. What you have to have, what you need. Okay, my have then comes from what I was given. I was given the whole 20 to 7. I was given 20 slices of bread to 7 slices of ham. Okay? So you could divide that out, and that means for every 1 slice of ham, I have 2.86 slices of bread. So this is where I could actually then just compare those two. And sometimes I kind of chant to myself what they mean. Like the first ratio is what I need. The next ratio is what I have. What I need, what I have. What I need, what I have. Okay? So I need 2 slices of bread for every 1 slice of bread, ham. What I have is 2.86 slices of bread. So can you see I can go ahead, and if I did this on my test, I would say bread is in excess. Why? Because I have more than I need. That's it. Bread is in excess using this technique. I don't know technique, but. So bread is in excess just by comparing those two ratios. That's just one way of identifying. And that's what we said before. We said bread was in excess and ham was in limited amount. That's it. So one of the emphasis of stoichiometric calculations and identifying the limited reactant is everything falls in place based upon the reactants that's there in limited supply. Okay? In the case of our sandwiches, it was how many sandwiches we could make based upon the ham. In the case of how much excess bread's going to be left over based upon the ham. So, okay, so here we go. Ham was the limited supply reactant. Okay, so like we saw a minute ago, kind of the bird's eye view, we cannot make any more than 7 sandwiches if we only have 7 slices of ham, and for every sandwich we need 1 slice. Okay, it just is not happening. So, kind of doing this with we use stoichiometric ratios. So actually, then this would look like this, where we would start out with 7 slices of ham over 1. 7 slices of ham over 1. And then we could lift the 2 slices of bread for 1 slice of ham, and that could be our next term. That's like our stoichiometric ratio. Oh, sorry. How many ham sandwiches can we make? So 1 sandwich per 1 slice of ham. Slices of ham cancel, we're left with units of sandwiches, which is making me hungry, which is 7 sandwiches. I got ahead of myself. So I think the last question was something about how much of the stuff that's in excess will you have remaining. Of course, it's bread. How much bread will you have remaining? You can only say how much bread is remaining after you say how much bread is used, okay? So actually, the bread that will be used, again, we're going to start with our limited supply ingredient, which is 7 slices of ham over 1. Okay, and now is when we're going to go the 2 slices of bread over 1 slice of ham. Your slices of ham cancel. We're left with slices of bread, which of course is 14. And that's what you guys would have told me before. We need to use 14 slices of bread. Bread's there in excess. We're coming up with what we need to use based upon our limited supply ingredient. So then the last thing, how much of the excess ingredient will we have left? Well, we'll take that 20 that we have, and from that we'll subtract 14, which is what we're going to use, and we'll end up with 6 slices of bread remaining. So this is very analogous to the real sort of chemical problems that chemistry problems we're going to work. So again, we can't do this last step until we do basically a stoichiometric calculation to see how much of the excess reactant we're going to use based on the limited supply reactant. All right. And I'm not going to belabor this much, but all the information you need is here. So basically, They want a handout, and it's going to have one title page, one page of instructions, 2 data sheets, and 4 sheets of graph paper. And as it turns out, like I said, I'm not going to belabor it, but as it turns out, the graph paper ends up being present in limited supply. But we could do it kind of like we did our ham sandwiches. Okay, now on to leaving the ham sandwiches and the reports and going to a little bit something closer to chemistry. So we can, this is a reaction, we'll be using this reaction here and there where everything is a gas. So nitrogen gas, hydrogen gas, and ammonia in this case is also a gas. Okay, so it's balanced. We have a 1 to 3 to 2 moles is our stoichiometric coefficients. So in this little video I'm going to show you, it's a little animation. I'm going to put the word have here, okay, and there are 6 molecules of N2. I'll just go ahead and say 6 molecules of N2, and there are 12 moles or molecules of H2. Okay, and we'll just let this little animation run. It ran at my desk, so I don't think there's any sound to it. Maybe there is. Okay, so like I've been saying, kind of the crux of this, it's not really its own little problem. I think it's just kind of a problem you do on the front end of stoichiometric calculations. Before you can really proceed with a stoichiometric calculation, unless they say something is an excess, you can't assume which one you're going to run out of first. So you have to identify your limited supply reactant and then let everything else fall from there. So like in the lab, the 2 experiments that you guys did on Thursday, in all cases, I guess, your limited supply reactant was your sodium bicarbonate, your NaHCO3. Okay, so let's look at this one again and do some ciphering. Usually, what's given is something like this. So let's write underneath the thing what information we have. I think chemistry problems, a lot of times there are so many numbers and they're associated with different things. So one of the things I like to do is just kind of pull out the number and in this case, write it underneath what it is. So for instance, nitrogen, 72.0 grams of nitrogen. Okay, 22.0 grams of hydrogen. Notice it doesn't say that one is in excess. So this sort of problem, you're going to have to see which one you're going to run out of first. Because right off the bat, it says which reactant is in limited supply, which is in excess. Okay, so, but question number 2, what mass of the excess reactant will remain, well, that's like number 3, what mass of ammonia will be produced? So ammonia is NH3. So actually, that's question number 3 up there. Now, we've done some calculations where I can go from mass of something to mass of something else, you know, ordinary stoichiometric calculation. But we can't we can't leave first base until we know which, the N2 or the H2, how are we going to which one are we going to use for our stoichiometric calculations. Okay. So here are the molar masses of everything. You guys have this good? Okay, that will be helpful. And this is just a reminder that if you have a problem like this on a test, you're going to have to show this work. Okay, so the way I would do it is this way. And I'll show you, there's two alternate ways to do it. I'll show you like the second to last slide in this part. So what I would do is I need to come up with halve, H-A-V-E, halve moles of my two reactants. So I can take the mass of N2, 72.0 grams over 1, use the molar mass of N2, which is 1 mole N2 over 28.02 grams N2. My grams of N2 cancel, rounded to 3 significant figures. Moles of N2 are 2.57 moles of N2. Okay, this is what I have. And do a similar thing for H2. So I had 22.0 grams of H2 over 1. I use the molar mass of H2, so I have 1 mole of H2 over 2.016 grams of H2. Grams of H2 cancel. We're left with moles of H2. Round to 3 significant figures, I have 10.9 moles of H2. Okay. So these are my halve. Okay. So one of the next things you're going to see on the next slide is basically I'm going to take moles of H2 divided by moles of N2. Okay, and you'd be like, well, which route do I need to go? Do I have to go moles of H2 over moles of N2, or could I go moles of N2 over moles of H2? I usually like I like the numbers greater than 1. So, okay, that was my halve. Okay. So, what we have is 10.9 moles of H2 for 2.57 moles of N2, just what we have. Now, what we need is another ratio, and it's going to be the 3 moles of H2 over 1 mole of N2. That's what we need. 3 moles of H2 over 1 mole of N2. Now I need to go ahead and use my calculator and divide this one out, okay, so I can get moles of H2 per 1 mole of N2. So if you divide 10.9 by 2.57, you get 4.24. So that means it's 4.24 moles of H2 for 1 mole of N2. And this is where, like I said, I kind of chant it back and forth, say it a few times. Okay, we need 3 moles of H2 for 1 mole of N2. We have 4.24 moles of H2 for 1 mole of N2. So it looks like this must be H2 is in excess, because we have more than we need. So once you get to that point, it's like a pre-calculation, I think, to clearly say, so H2 is in excess, N2 is in limited supply, then you can actually answer the rest of the questions using the N2, okay, the nitrogen. Okay. So it's just, like I said, there's 2 other ways to identify which one was limited, nitrogen or hydrogen here. But whatever of the 3 methods you use, you have to show how you do it and clearly say your conclusions. Okay, so H2 is in excess, N2 is in limited supply. So now we can answer those 3 questions. 4 questions? So what mass of the excess reactant, which now we know is hydrogen, will remain after the reaction has been allowed to go to completion? So here's where I said you need to do your stoichiometric calculation based on the amount of H2 that will react. So notice one thing right here, and some problems in chemistry kind of lend themselves to this. I don't have to go back to the grams of nitrogen. Okay, it's nitrogen is in limited supply. I can actually just pick off the moles of nitrogen I had before. So moles of nitrogen, this is what I have. It stoichiometrically reacts with hydrogen on a 3 moles to 1 mole basis. So that's my next term. 3 moles of H2 to 1 mole of N2. Moles of N2 cancel. Okay, we're left with 3 moles of H2. Okay, so I can't remember. I think I'd go ahead and take this to grams. So we can use the molar mass of H2, which is 2.016 grams of H2 per 1 mole of H2, to get from moles of H2 to grams of H2, and then that's it. But remember, now this sort of calculation, again, in chemistry, sometimes you work things in steps, and to me, you really kind of need to label this step as mass of H2 reacted. Because then you're like, oh, okay, so how much is remaining? Well, I'll take what I have minus what was reacted. So rounded to 3 significant figures, 15.5 grams of hydrogen is what reacted with this limited reactant. Now let's say you get down here and you end up with a mass that's greater than what you started with, then you must have misidentified your limited reactant. It happens to the best of us, okay? So we're not quite done to answer the question. Again, now all we need to do is take our have amount, okay, which was at 22.0 grams, minus 15.5 grams. And now we round according to decimals, which is 1 decimal. Okay, so that gives us 6.5 grams of hydrogen left over. That's a lot of work. Okay. Then the next question. What's the next question? What mass of ammonia, this is the last one, what mass of ammonia will be produced? Now there's a few compounds in general chemistry that we deal with. Ammonia is one of them, so NH3, if you could kind of, NH3 is ammonia, that might help. So it's just kind of an ordinary stoichiometric calculation now. Again, we don't have to backtrack to grams of N2, although we could, and sometimes I have. But earlier on in our work, we have moles of N2. So now I'm trying to get to mass of NH3, so I'm going to pick off these stoichiometric coefficients of 2 moles of N3 for every 1 mole of N2. And that's what's going to be the ratio. 2 moles of N3 over 1 mole of N2. Moles of N2 cancel. We're left with moles of NH3. So, but we want grams, so then we need to go back a few slides and pick up the molar mass of NH3. 17.03 grams per mole. So 17.03 grams NH3 per 1 mole of NH3. And that should do it. So we have units of grams of NH3, which is what we're after. Round to 3 significant figures. Then the mass of NH3 is 87.5 grams. And that's it. And I did pull a question for you guys to work on for Wednesday on like this. It's a classic. So that was one method, coming up with a ratio of what you have, HAVE ratio, versus what you need, and then go from there. See which one, see if it's in excess or limited supply. Here's one. You could do a stoichiometric calculation to see which one or the other one you would need. So it looks kind of like this. Like again, if you have A reacting with B to go to form C, and you're given X grams here and Y grams here, you actually could do a stoichiometric calculation based on that and find out the grams of that you would need. Find out the grams based upon this given grams of A, okay, how many grams of B would you need? And then see if you have extra B or not enough B, and kind of make your conclusion that way. This one I've seen students like to do. This one seems like could be potentially a lot of work, but it's pretty straightforward. I like this one too. So again, if you have two reactants going to form a product, and you have X grams here, Y grams here, okay, what you do basically is, in this case, a pair of stoichiometric calculations. You take A and find out how many grams of C you would get, and then you take B and find out how many grams of C you would get. And whichever one is less, that's there in limited supply. That's kind of how we did, I think, just eyeball the whole ham sandwich thing a little bit. So that's fine too. Okay, but you need to show your work and clearly identify which one is in limited supply. So this is a busy assignment slide. You do the first two questions, 63 and 64, and we'll take a look at them in here a minute. And then you need to add 69. So they're all in chapter 4. 463, 64, and 69. Yep, and then skip 65 and 66 for now. They deal with solutions, which we haven't gotten there yet. So it looks like we are going to talk about yields here in a minute. So let's take a look at, if I can find it. Nope, wrong one. This one. Okay. So the problem with 63 and 64 is they're kind of like more basic than the problem we just dragged ourselves through with the nitrogen and the hydrogen going to form ammonia. So how many moles of NO can be produced if you're given the moles of NH3 and O2? Okay, so those are have amounts. Okay, so my hint for that one is you can see what you need, right? You need 4 moles of NH3 for every 5 moles of O2, right? So first you need to identify the limited reactant, one of 3 ways. And like I've been doing the whole compare moles of O2 to moles of NH3, okay? What you need versus what you have, or one of those other 2 alternate ways. But you need to clearly identify which of these 2, NH3 or the O2, you're going to run out of first. Okay, and then to finish it up, do ordinary stoichiometric calculation using the half moles of the limited reactant as your first term. Okay, so that was all I need to say about that one. Okay, this one I'm glad to give you a heads up. If you're not one that necessarily looks at my solutions, okay, they're not solutions, my hints, you might want to jot down this first step. It's not balanced, but actually this is calcium hydride reacting with water to form calcium hydroxide and hydrogen gas. So we haven't necessarily talked about nomenclature a lot, so this is pulling the text out and giving it into an equation. So other than that, it's very similar to 63. Okay, so your half moles are 0.82 moles of calcium hydride, 1.54 moles of water. That's what you have, right? And you're supposed to get the moles of H2 produced. So similar to 63, you need to balance, the equation, identify the reactant that's there in limited supply, either the calcium hydride or the water. Okay, compare a have and a need ratio, or show your reasoning. How do you know which one's the limited reactant? And then go ahead and proceed with an ordinary stoichiometric calculation based upon the limited reactant to get to moles of H2. Again, this one's different than the one we pulled ourselves through because you don't have to mess with grams. You're just straight moles. Life is simple. So that one's not too bad. Easy for me to say. Now, so if those weren't too bad, then this one must be bad. And it's not terrible bad, but, okay. So this is very, very, very similar to the nitrogen, hydrogen goes to form ammonia that we just did. So now instead of moles, we're given mass. Actually, we have 33 grams of both. And you will need to balance this equation. Ammonium chloride, NH4Cl goes for plus, calcium hydroxide, Ca quantity OH2. The delta, of course, is heat to form ammonia, NH3, plus calcium chloride, CaCl2, plus water, H2O. So you need to balance that puppy. That's the first step. You're going to need to convert grams to moles. Make sure that you show the molar masses calculations. Determine which reactant is limited supply, because then that's how you're going to take off and do your other calculations. Notice this is very similar. It says basically how many grams of NH3 will form, that's A. And for B, which reactant remains in excess and what mass. So, okay, my hints were then go ahead and do ordinary stoichiometric calculation once you've identified your limited reactant. Okay. So for B then, you need to perform another stoichiometric calculation to see how much of the excess supply reactant that you're going to use, and then you're going to do subtraction. You're going to start with what you have minus what you're going to use. That will tell you how much you have in excess. So that's a good one. They're all good. All right. So let's take a look. A lot of times the yield lecture is kind of, well, you'll see. That's not too bad. This actually, I kind of feel like we talked a little bit in lecture about it. Okay, percent yield. So whenever you do a stoichiometric calculation that looks like this, A plus B goes to form C, and you are given the mass of a reactant and asked to find the mass of a product like that, that is a theoretical yield. You are coming up, that is a yield calculation. Theo is theoretical. Okay, that's it. Oh, sorry, I did that wrong. Like, how could you have 2 question marks? Sorry, I'll change that first question mark to an X. You know the mass of the limited reactant. Final answer. So this slide says that your theoretical yield actually is an upper limit. So usually, and I'm going to give you several reasons why, what you actually come up with in the lab is usually under what you should come up with. Okay? Unless it's a copper lab, which is what you guys are going to do on this week. So these are 4 reasons why your yields should be low. These are 4 reasons why your yield that you get actually is what we call actual. Okay? Actual yield. Sometimes I call it experimental yield. This is basically why you don't get back in the lab what you think you should get back on paper and pencil, your theoretical yield. So we'll talk about each one of these. Starting with reaction kinetics. So I was thinking of in my office how to describe this, and A plus B goes to form C. Now if you take general chemistry 2, we're going to be talking more about, I don't have a symbol for it, we're going to be talking more about how sometimes these things take a lot of time for A and B to react to go to form C. The study of how long things take is actually reaction kinetics. And it's kind of cool because you're looking kind of behind the scenes of what's going on behind the scenes. But anyway, basically we're not patient enough. So I have a graph to kind of show you what that would look like. So right here in red, we have reactants. Now, along the y-axis, we have time. So basically, you start out with all these reactants and your amount of reactants, and along the along the y-axis is concentration. So the concentration of your reactant goes down over time, and of course, then the concentration of your product, okay, goes up over time. So P is product. Okay. So what this says is if we were to go ahead and we only have 7 seconds and we basically squelch our reaction, okay, it looks like this. This down here be 7 seconds, go up. Okay, basically about 7 seconds we have, about half of our reactants have been converted to products. So we're not there yet. You know, we definitely would not get if we stopped it right there. So that's reaction kinetics. Another one is chemical equilibria, which is awesome. It's another general chemistry 2 thing. So again, A plus B goes to form C. You know, that looks familiar. Well, there's a lot of situations out there where actually then C goes back and what decomposes to form A and B. Okay, so it's basically a 2-way street. Reactants go to form products, and products also go back to form reactants. Like, how could you win with that, right? So you're definitely never going to get 100% yield. So here actually is an example of a chemical equilibrium up here. Okay. If we go ahead and call these reactants on the left and products on the right, which is kind of the convention, even though they are going back and forth. Okay. Here we have the reactants here. Okay, getting less, the I2, the H2 and I2 getting less, going down in concentration. Okay, but notice that they level off about here. Okay, and the product going up in concentration and it levels off about here. Chemical equilibria totally rock because then about here actually we say that an equilibrium has been reached. Not to say it's not dynamic and reactants are going to form products, products are going to form reactants, but their concentrations are steady. When we, is that Gen Chem? I'm getting I think it might be Chem 2 that we study actually pH, because it's only when we talk about chemical equilibria, after we've talked about reaction kinetics, I think, can we talk about pH, because pH is one big chemical equilibrium. All right. So another thing that can happen, I don't know if I have anything necessarily clever here, but like your A plus B that you're hoping to go form C, here's one for you. And actually, when you guys did your magnesium oxide reaction, your magnesium, which we could say is A, also could react with nitrogen instead of oxygen. A plus D goes to form E, okay? So basically, if your reaction of interest is 1, your reaction of, or competing reaction would be 2. Okay, it's basically, you didn't want it to happen, but it happens. It happens anyway. Physical losses, one of the things in pharmaceuticals especially, anything you like put directly into our bloodstream needs to be very, very pure. And in order to purify things, you actually kind of tend to just take for granted that you're going to lose the active ingredient or the ingredient of interest along the way. Physical losses that are just inherent, and if you guys know what the word inherent means, it means you can't get away from it, inherent to your experimental design. Okay? So this, I guess, speaks more to the pharmaceuticals, but it's a trade-off between purity, usually, and losing your product. All right, so theoretical yields then, remember, are just an ordinary stoichiometric calculation where you know the mass usually of a reactant and you're finding the mass of a product. That is your theoretical yield. So theoretical yields would always be the case if all of your limited supply reactant was consumed, okay, if it only reacted by the reaction of interest, okay, and if you were able to get all the product after you made it. So the stars don't always align that way. Okay, so physical losses and gross error. Now, gross error is something that is avoidable. And you might say, well, I couldn't avoid it, but yeah. Avoidable. Gross error is not inherent to your experimental design. Okay? I hate to use the word ineptness because that sounds so mean, but it's the ineptness of the investigator that has caused it. I say it's avoidable, but at the same time, I don't know, it happens to all of us. So like if you spill some of your, along the way, say you have a series of chemical reactions like you're going to do on Thursday, and if you spill something here or there, then that's a gross error, you know. It's not really terribly bad, but you're going to get lower yield than you should, okay? If you misread a measuring device, if you make an error in your calculation, you don't follow instructions. But again, it happens to the best of us. So let's get to the calculation, or another calculation. So I think you guys are going to do this for your carbon dioxide in your sodium bicarbonate lab. Okay, so percent yields are always your actual, and again, sometimes I'll call this experimental, just kind of how I learned it. Actual or experimental, they're the same thing, what you actually got. Okay, that will go in the numerator, and then you'll divide that by your theoretical yield. And just to remind you, your theoretical yield comes from stoichiometric calculations. Okay, so that's the paper and pencil stuff. What you really got divided by what you thought you should get times 100 to get it in parts per 100. Notice that you can actually go in grams or leave it in moles. Either way will be fine. Usually it's in grams. So we're going to do one example here. So this is one that we actually did on Friday. So we said if you have 1.25 grams of Cl2 and sufficient, i.e. excess, P4, then we said ordinary stoichiometric calculation says that we should produce 1.61 grams of product. That was just, okay, that's just a stoichiometric calculation. Let's say in your lab that you actually only came up with 1.08 grams. So this is your actual yield. Sometimes in chemistry problems, it just takes a minute to identify what the numbers are. So our actual yield is 1.08 grams. Okay, and our theoretical yield is the 1.61 grams. What is the percent yield? So we're going to divide that by that. Okay. So percent yield is 1.08 grams, which is what we actually got, divided by 1.61 grams, which was our theoretical yield, times 100% rounded to 3 sig figs. We got 67.1%. A lot of times if you're reading these scientific experiments where a lot of times they will tell you what the average yield is, and it's not necessarily 100%. So these will also be due on Wednesday. We'll take a look at these. '73, '74. Nope, that wasn't it. Maybe it was. Okay, so this one, it's kind of straightforward. It says that you have 277 grams of CCl4, excess HF, and your experimental yield of the CCl2F2 is 187 grams. Okay, so I don't have a whole lot to add to what we've been talking about. Oh yeah, I guess I do. So it says you're supposed to come up with the theoretical yield of CCl2F2. So the theoretical yield is just an ordinary stoichiometric calculation. You don't have to identify what's in limited supply because they already tell you. Then the actual yield, sometimes that throws students off. The actual yield is 187 grams. No calculations needed. And then percent yield would be the ratio. So that one's pretty good. The next one looks like this. Parts A and B are very similar to 73, A and B. So ordinary stoichiometric calculation for A, that would be your theoretical yield. For B, your percent yield, same as number 74B. For For C, I just went ahead and, again, I'm going to post these like I usually do. I had to go back to my notes. I hate the C part on this one. So, for what it's worth. So I went ahead and, there's different ways to skin this cat for C, but that's probably the easiest. Okay? All right.